Hello again. So this is our fourth lesson in the series of finite element method for CFD problems. So in this lesson we are going to look at how to solve this steady state diffusion equation in 2 dimensions using the finite element method. Okay, so we are all familiar with the diffusion equation. So in the short form, we can write the steady diffusion equation where u is the diffusion variable, the variable that we are interested in solving, and mu is your diffusion coefficient, and f is the source term. Okay, here nabla is the gradient operator and nabla dot is the divergence operator. Okay, so in a typical two-dimensional problem, we have the domain given by the given by omega, and it has boundaries, a set of boundaries, and the entire boundary consists of either a Dirichlet boundary or a Neumann boundary. So on Dirichlet boundary we have the solution specified, that is U specified, and the Neumann boundary we have the kind of fluxes specified. Okay, so this round in PDE for study diffusion equation is supplemented with a set of boundary conditions. So like a Dirichlet boundary condition, okay, where we know the variable, okay, the value of the variable on the part of the boundary gamma d, and the Neumann boundary condition where we know the normal flux and the Neumann part on the Neumann boundary gamma n. Okay, so g and h can be 0 as well. Okay, so they need not be non-zero. Okay, so in full form, by expanding this nabla, that is the derivatives, we can write the equation in this form. So like this is a second order partial differential equation, and here we are assuming that the diffusion coefficient mu is a constant. So that is why it is outside the derivatives. Okay, so you should be familiar with this equation. Okay, right. Now what is the first step in finite element method? In the finite element method, first we derive the weak form starting from the strong form, that is the partial differential equation. Okay, so we have the diffusion equation. So let us take the simplified case, that is we assume that the diffusion coefficient is constant throughout the domain. So we take the mu out of the derivative. Okay, so then we apply the weighted residual statement. We use the weighted residual statement, which is the integral of product of the weight function and the residual. Okay, that is the integral over the domain should be equal to 0. Our residual is residual of the PDE. Okay, so we take the source term to the left hand side, so it becomes minus f. Okay, so our residual, in this case our residual is a scalar. Okay, we have only one PDE, so our residual is a scalar. And then we apply the integral. Okay, we apply the integral to both terms, and we split the integral, then we take the source term integral to the right hand side. Okay, so we know f, so we can evaluate it. Okay, there is no unknown in f in the right hand side. Okay, so we take the integral of wf to the right hand side. Okay, so just a minor correction here, it should be dA. Okay, we are operating in the second dimension, so we have areas. Okay, right. Okay, dA corresponds to the area integral. Okay, now once we have this integral, okay, once we split the integral, we have to apply the boundary conditions. Okay, in order to apply the boundary conditions, and we made some assumptions about the function space for u. Okay, so we assume that u, the solution u, the variable u is a sum of u bar plus g. Okay, so there is a lot of literature about why we do this. I'm not going into the details here. If you want to learn more about the weak forms and why we split it like this, I have another video on deriving the weak forms for generic boundary conditions, and there I explain why we do this. So there is a link to that video in the description of this video. So please watch that video if you want to learn more about why we do this. Okay. In brief, the reason we do this is because for problems with non-homogeneous Dirichlet boundary conditions. When we have non-homogeneous Dirichlet boundary conditions, when like we have to choose the function space for U such that it's still okay. So for U and W such that they still satisfy the vanishing boundary condition on the Dirichlet part of the boundary. Okay, we cannot do the directly on U because U equal to G on the Dirichlet boundary. So what we do, we split it into U bar plus G, where U bar satisfies the homogeneous Dirichlet condition, that is U bar equal to 0 on the Dirichlet boundary and G equal to G on the Dirichlet boundary. Okay, so in this way we have test function satisfying the homogeneous Dirichlet boundary conditions on the Dirichlet boundary. Okay, and by using this, that is U equal to U bar plus G, and substitute it here, we simplify the integral and we take the integration by parts. We do the divergence theorem, we apply the divergence theorem, and we get this integral, which is the weak form. If you notice here, so since we have U equal to U bar plus G, so if we substitute here, we get G term and we take it to the right hand side, because we know G. Okay, and we take it to the right hand side after applying the divergence theorem. Okay, that is why we still have minus here. When we apply the divergence theorem, this minus becomes plus. Okay, when we apply so when we apply the product rule, okay, this minus becomes plus, and then once we take it to the right hand side, we still get minus here. Okay, and when we apply the divergence theorem for the Neyman boundary, we get this part. Okay, so that is why we have dl here. This is the line integral on the Neyman boundary. Okay, so like to learn more about how to derive the weak form, especially for problems with non-zero, that is inhomogeneous boundary conditions, watch the other video. Okay, so this is the generate weak form for the study diffusion equation with non-homogeneous Dirichlet boundary conditions. Okay, the application of Dirichlet boundary conditions is going to be the same. That is, we multiply the column in the stiffness matrix with the corresponding value of the specified value for that degree of freedom. Okay, so the application is going to be the same. So in order to avoid the derivation further, I am going to assume homogeneous Dirichlet boundary condition, that is U equal to 0 on the boundary. Okay, so in that case, we get rid of the terms corresponding to capital G coming from the non-zero Dirichlet boundary condition. So first, if you understand the formulation and the distillation for the homogeneous Dirichlet BCs, extending it to non-homogeneous Dirichlet BC is straightforward. Okay. Now this is our weak form. Okay, in vector form. Okay, so here instead of dot product, I have transpose on nabla W. Okay, nabla W is the gradient, so this is a vector, so we need a transpose to get a scalar quantity. Now after this point, we discretize the solution U as well as the test function W. Okay, so that is, we discretize means we use the finite element approximation as U equal to n1 u1 plus n2 u2 plus and so on nn un. Okay, that is, we have n number of basis functions and n number of unknowns, and we put this in our matrix vector form. Okay, here n is a vector of one row and n columns. Okay, capital N is the basis function matrix and capital U is the basis function, the degrees of freedom vector. Okay, so this is exactly like what we did in 1D case. Okay, and then we calculate the derivative. Okay, so that is nabla u, dou u by dou x and dou u by dou y. Since we are in 2D, we have only two derivatives. Then this is our gradient field matrix, capital G, and this is our u, the vector of degrees of freedom. Okay, bold u. Okay. Similarly, for the test function, we use the same basis functions. Since we follow the Delarkin method, we use the same set of basis functions for the solution variable and the test function. So we have the same here n. And similarly for nabla w, that is for gradient w, we have g w. Okay, this g is the same g here. Okay, and then once we substitute for u, that is u equal to n multiplied by u, these are the matrices, and nabla u, that is gradient u equal to gu into our vector form of the weak form. Okay, so here we are substituting del w, we are substituting for del w gw, and for del u gu, and for w we are using this transposed form. Okay, on the right hand side, and then we take w transpose from all the terms. We can write it in this form, and for an arbitrary w bar, we should this integral multiplied by u should be equal to the term inside the bracket. This is our ku equal to f. Okay, so this term on the left hand side inside the bracket is our stiffness matrix. This term in the brackets on the right hand side is our force vector. Okay, and once we apply this to element level, that is by looking at the element level, we have element stiffness matrix and element force vector. Okay, so this is our element stiffness matrix and this is our element force vector. Here the element force vector has two parts. One is coming from the source term f and the other one is coming from the Nyman boundary condition h. Okay, this is like specified flux. Okay, now the beauty of the finite element method is that if the Nyman boundary term h is 0, then we do not need to do anything for this integral. Okay, we simply ignore this integral for all the boundaries where h is 0. Okay, so this is the one advantage of using the finite element method. So when h is 0, we do nothing, like, okay, so this is a do nothing boundary in finite element method. Okay, and here we have our boldface n the matrices. Okay, and G is our gradient field matrix. Okay, now we don't evaluate these integrals explicitly, that is using analytical methods, because they become quite difficult as the element becomes more complicated in terms of the how it is oriented. Okay, if you have a body aligned like axis aligned element, it is easy to evaluate, but if you have an arbitrary oriented element, the integrals are difficult to evaluate. That is why we use Gauss points to integrate the element stiffness matrix and element force vector. Okay, so how we do that? We transform the integral from the physical domain omega e to the element parent domain, that is local domain omega hat e, and then so in omega hat e the integrals are in xi and eta coordinate system. This is our local coordinate system for 4 noded element. For example, let us say we have the 4 noded element. Okay, so it has 4 nodes, and in the local domain our parent or local coordinate system is xi and eta. Okay, so we map the integral from the physical coordinate system omega e to the local coordinate system omega hat e. Okay, so this determinant of j, it gives us the mapping. Okay, j gives us the mapping and determinant of j tells us the change in the area from the physical domain to the local domain. And again, even when we are in the local coordinate system, we don't do the integration explicitly, we use the draw points here. Okay, so instead of integral, we have the loop over draw points. This is the summation, so like a loop over draw points, and at each draw point we evaluate all these terms and then keep on adding them to the element stiffness matrix. So for integrating the element stiffness matrix and this force vector due to source term, for this 4 noded element we use 4 draw points, and for these are the coordinates of the draw points, and all the 4 draw points have a weight of 1. Okay, if we change a different, if we use a different draw point rule, then the weights will be different, but for this 4 noded element this 4 point rule is sufficient enough. Okay, so in the upcoming lessons we are going to see how we implement for the 4 noded element, like how to calculate the element stiffness matrix and force vector. Okay, so to implement this, what do we need? We need to calculate G. We need to know like what this G matrix is. We need to know what this Jacobian matrix is. We need to know what the weights are. And in order to calculate G, okay, so we need to know what the derivatives of basis functions are with respect to x and y. Okay, so now let's look at the pseudo code before we actually implement this. Okay, so in the for loop, for the draw point, what do we do? What do we need? Okay, so in order to know what we need for in the for loop for draw points, okay, now we need mu, we need g, we need j, that is the Jacobian, we need the weight. Okay, now how do we calculate them? Now before we go to the pseudo code, let's look at the global to local mapping in detail. Okay, we have the element in the global coordinate system. Okay, it has 4 nodes and the orientation is counterclockwise direction. So 1, 2, 3, 4. That's because our basis functions we store them in counterclockwise direction 1, 2, 3, 4 in the local coordinate system. Okay, so this is our mapping. Now for this we use this interpolation. Okay, this is isoparametric element because okay, so we are using the same set of basis functions for the geometry, that is coordinate x and y, as well as for the field u. Okay, we are using the same set of basis functions, so this is an isoparametric element. And for the 400 element, we know the basis functions, we can derive them if you want, but we are not going into those details, okay, in this course. So these are the basis functions in the xi and eta coordinates, that is our local coordinates. And once we know the basis functions in xi and eta, we can find their derivatives with respect to xi and eta. These are the derivatives. Okay, so once we know the derivatives of basis functions with xi and eta, and by following these expressions for x and y, we can calculate the Jacobian matrix. Okay, this is our Jacobian matrix: dou x by dou xi, dou y by dou xi, dou x by dou eta, dou y by dou eta. Okay, so how do we calculate dou x by dou xi? We know x, and we know that n1, n2, n3, n4 are functions of xi. So we have, okay, so dou n1 by dou xi x1, dou n2 by dou xi x2, and so on. So we have a sum from I equal to 1 to 4, dou ni by dou xi xi. Okay, similarly for dou y by dou xi, we know y. Okay, using this we have this term. Similarly for the other two derivatives. Okay, so once we know the coordinates x1, x2, x3, x4, y1, y2, y3, y4, and once we know the coordinates of the draw point, we calculate these derivatives of basis functions with respect to xi. Then we evaluate the Jacobian. Once we know Jacobian, we can calculate the basis function derivatives with respect to physical coordinates x and y. Okay, and then once we know the basis function with respect to x and y, we have our G matrix. Okay, since we are using the 4-noded element, the G matrix will be of size 2 by 4. Okay, 2 for the 2 derivatives and 4 for the 4 basis functions. Okay, 2 by 4. Okay, so this is the information that we need to evaluate our stiffness matrix. Okay, now let's look at the pseudocode. Now we said we use 4 gross points, okay, for evaluating our stiffness matrix, and the fourth term corresponding to the source term f, small f. Okay, so what do we do for each gross point? That is, in the gross point loop, first we need to know what the coordinates of j and eta are and what is the weight corresponding to each gross point for that gross point. Okay, so we have 4 gross point and these are the coordinates of j and eta. Okay, so for each gross point we know j and eta. Once we know j and eta, we can calculate the basis functions n and also their derivatives with respect to j and eta. Okay, so these are these. Okay, once we know j and eta, we can calculate n1, n2, n3, n4 and their derivatives using these expressions. Okay, once we know n and their derivatives, we can calculate the Jacobian matrix. Okay, so we multiply the derivatives of n with respect to j and eta with the coordinates, that is x and y coordinates, and then we can evaluate these expressions to find the entries of the Jacobian matrix. Once we know the Jacobian matrix, we can find its derivative. Sorry, we can not the derivative, we can find its determinant. Okay, once we know j, and once by this point we already know dou n by dou j, dou n by dou eta, we can find the derivatives with respect to the physical coordinates x and y. Once we know this derivative dou n by dou x, dou n by dou y, we can form our G matrix and then evaluate the stiffness matrix. So we keep on adding this term to the stiffness matrix. So this is our mu, the diffusion coefficient G transpose G, J is our determinant of the Jacobian matrix, and omega is the weight. Okay, and we keep on adding to the stiffness matrix. Similarly, the force vector, we know n. Okay, this n transpose f is given to us, what is the source value, and j omega. So this is how we evaluate the element stiffness matrix and element force vector in a for loop over the gross points. Okay, in the next lesson I will show you an example, okay, before we actually code for solving the problem.